No good. What it does instead is it very rapidly equilibrates into a non-planar conformation, which looks a bit like a boat. It's called a boat conformation or tub conformation. And the tub conformation is non-planar. A non-planar conformation. This is kind of a side view of that tub non-planar conformation, but you can see even in this side view that the p orbitals making up these pi bonds would sit somewhere something like this, whereas the p orbitals down here would be straight up and straight down. They're almost orthogonal to each other, maybe not quite orthogonal, but close to it. They're definitely not parallel to each other, and the molecule is definitely not planar. So back to Huckel's rules. The molecule is cyclic, and it's fully conjugated in as much as it has an atomic 2p orbital at every carbon atom, but it's not flat or planar. So it's not obeying Huckel's rules for aromaticity, and now we see why this line is in there. Why it is that it must be flat or planar, because if it's not, then these p orbitals are not communicating with each other. For this particular molecule, that's a good thing, because if it was flat or planar, and these molecules and these p orbitals were all communicating in this fully conjugated pi system, we'd have a problem. We'd have an anti-aromatic molecule. But this molecule in this conformation is no longer anti-aromatic because it doesn't obey one of the first three rules. It still has 4n pi electrons associated with it, but it does not obey this rule right here. Anti-aromatic molecules, remember, they obey Huckel's first three rules, but they have 4n pi electrons. So that's the definition of an anti-aromatic, an unusually unstable molecule. This structure over here is not obeying the first three rules. So what is it? It's not aromatic, and it's not anti-aromatic. Actually, it's non-aromatic. We can classify all molecules as one of the following three things. They're either aromatic, which means they obey all of Huckel's rules, benzene being the prototypical example, or they're anti-aromatic, which means they obey the first three. They're cyclic and fully conjugated and flat, but they have 4n rather than 4n plus 2 pi electrons. Or we now realize they can be non-aromatic, which means that they don't obey one or more of the rules. It turns out that most molecules fall into this category. So they're either not cyclic, or they're not fully conjugated, or they're not flat, or they don't have 4n or 4n plus 2 pi electrons associated with them. Many molecules, most organic molecules that we've worked with over the months we've been studying organic chemistry, or weeks we've been studying organic chemistry, are non-aromatic. Just think of all the alkanes you've ever studied, like butane. It's not even a ring, it's not cyclic, so it fails one of those early rules right away. It's not aromatic, it's not anti-aromatic, it's just non-aromatic. So it turns out that we can define pretty much all organic compounds as one of these three things: aromatic, anti-aromatic, or non-aromatic. And cyclooctatetraene in this tub conformation is just simply non-aromatic. So what do you do if you see this cyclooctatetraene on an exam? Well, the key is, how is it drawn? You see, if I hold it in this flat conformation, in this conformation it's anti-aromatic. It obeys Huckel's first three rules, and it has 4n pi electrons. It's definitely anti-aromatic there. But if it's drawn like this, in this non-planar conformation, now it's non-aromatic. So you'd have to be very careful about how the molecule is drawn. On any exam question that I would ask, I would always be very clear about which structure you should be considering. If I draw this structure, for example, I would say consider the molecule exactly as drawn. And in this case it's flat. Or if I drew this structure, exactly as drawn is non-planar. So this one's non-aromatic and this one's anti-aromatic. I hope that makes sense to you. Okay, couple more. So we wrote this one down as anti-aromatic because as drawn, it's flat. So this is correct. As drawn, that's anti-aromatic, but we know that it can adopt a non-planar tub conformation, which would be non-aromatic. Well, these two are also drawn as flat structures, cyclic, fully conjugated. So the only question is how many pi electrons are associated with each of them? Well, let's count up the total number of carbons here. 1, 2, 3, 4, 5, 6, 7. So there's 7 carbons. Each of them would have an atomic 2p orbital associated with them. That's what the circle means. It's fully conjugated. That would add up to 7 electrons, but the negative charge means there's an extra electron in there, so there's 8 pi electrons here. This one would have to be anti-aromatic. Anti-aromatic because 8 pi electrons is a 4n rather than a 4n plus 2 number. Let's go to this one. This is that 8-membered ring again, fully conjugated, so there's 8 atomic 2p orbitals associated with it. If it were neutral, it would have 1 electron in each of those 8 orbitals, which would add up to 8 electrons, but it's 2 minus, which means there's 2 extra electrons floating around in that pi system. It's not 8, it's actually 10 pi electrons. And that is a 4n plus 2 number. When n equals 2, 4n is 8 plus 2 is 10. This molecule is aromatic. So we can look at any of these structures and we can define them as either aromatic, anti-aromatic, or non-aromatic. And we've done that for these compounds right here. Very useful, very helpful to use these tools in order to figure it out. Okay, this brings us to the topic of heteroaromatics. Now, heteroaromatics means there's a heteroatom somewhere in the aromatic ring, and we define a heteroatom as something other than carbon or hydrogen. In this case, it's nitrogen. This looks just like benzene, except one of the carbon atoms has been replaced by nitrogen. That nitrogen is neutral. Nitrogen should have 5 valence electrons to be neutral. This nitrogen, like most neutral nitrogen atoms, has 3 bonds, 1, 2, 3, plus a lone pair, adds up to 5 valence electrons that it formally owns. It's neutral. Down here we have pyrrole. It's a 5-membered ring. Again, the nitrogen has 1 bond, 2 bond, 3 bonds, and a lone pair. It's neutral. Down here we have furan. It's a 5-membered ring, and there's an oxygen. The heteroatom is oxygen rather than nitrogen. Oxygen should have 2 bonds and 2 lone pairs, should have 6 valence electrons. 1 from that bond, 1 from that bond is 2, 3, 4, 5, 6 from the lone pair electrons. All of these compounds are neutral. There's no charge associated with any of them. Well, are they aromatic? I guess I've given it away by calling them heteroaromatics up here at the top. They are, in fact, all aromatic structures. We have to understand, why are they aromatic? What is it about them that makes them aromatic? Well, the thing that makes them aromatic is going to be the same thing that made any of the other molecules we've been looking at aromatic. They have to obey Huckel's rules for aromaticity. Let's look at Huckel's rules. They have to be cyclic. It is. They have to be fully conjugated. How do I know if that nitrogen is fully conjugated? Well, in this case, it's very easy. It's fully conjugated because it's part of a carbon-nitrogen double bond, and that means that it must be sp2 hybridized. Whenever you see a heteroatom that's part of a double bond, it, just like carbon, must be sp2. And since it's sp2, it has to have an atomic 2p orbital on it, and all the other carbons around the ring have an atomic 2p orbital associated with them. That's our definition of fully conjugated. Every atom around the ring, including one that's not carbon, is sp2 hybridized with a 2p orbital available for conjugation. So it is fully conjugated. It's cyclic and it's fully conjugated, and it's flat. You can see I've drawn it as a flat structure. So it obeys the first 3, and then we get down to 4n plus 2 pi electrons. Well, let's count up the electrons. There's 2, 4, 6 pi electrons. What about those lone pair electrons? if those lone pair electrons were in the pi system, they'd have to be counted as part of the pi system, and there would actually be 8 pi electrons. That would make it anti-aromatic. 8 is a 4n number, not a 4n plus 2. What's going on here? So what I would like to do now is I would like to do the same thing I did with benzene a while ago. I'm going to spin this molecule a little bit and then draw it in this fashion, coming out of the paper. So I basically spun it and turned it up. And when I do that, it allows me to see all of the atomic 2p orbitals associated with all of these atoms around the ring. And look, the nitrogen carbon has a double bond, which means there must be one electron associated with those 2p orbitals, and that goes to form that double bond. And then there's these other double bonds that are indicated here, so we could draw something like this. That's a good, different, but a good structural picture of this molecule. We can see those p orbitals clearly. What about that lone pair? Where the heck are they? Well, one thing's clear, they're not part of the pi system. I've drawn in the pi system, and they're not there. Where are they? Well, since this is an sp2 atom, just like all of the carbons, that nitrogen's going to have 3 sp2 orbitals available for 3 bonds, but in the case of nitrogen, it doesn't want an extra bond. It's happy with just 3 bonds total, including the pi bond. So the lone pair is just going to sit in an sp2 orbital. There's the lone pair. And we know, structurally speaking, that the sp2 orbitals are also used to make up the sigma bonds, the carbon-nitrogen single bond here, the carbon-nitrogen single bond there. Those are made up of sp2 orbitals on nitrogen overlapping with sp2 orbitals on carbon. So like every sp2 atom, this nitrogen has 3 sp2 orbitals available. But this third one, unlike the case with carbon, doesn't participate in a new single bond. It just sits there with a lone pair in it. This nitrogen has a lone pair that is orthogonal or perpendicular to the pi system. Since it's orthogonal, it has absolutely no communication, no interaction with the rest of the pi system. The number of pi electrons is simply 6. 2, 4, 6. The lone pair is not part of the pi system. There are 6 pi electrons in this molecule. The lone pair is outside of the pi system. This is indeed an aromatic structure. In order to really understand that, you have to understand what it means to be sp2 hybridized and what we do with those 3 sp2 orbitals that are part of sp2 hybridized systems. If it were carbon, we would use those sp2 orbitals to make 3 single bonds. Look at this carbon here. Makes a single bond to nitrogen using an sp2 orbital, makes a single bond to hydrogen using an sp2 orbital, and makes a single bond to another carbon using an sp2 orbital. And then the p orbital that's left over coming in and out of the plane of the board overlaps with a p orbital here to make the pi bond. Nitrogen's the same way, except it doesn't form a third single bond. It only forms 2 single bonds, one there and one there, and this last sp2 orbital is just used to house the lone pair. Structurally, we know that those orbitals, the sp2 and the p's, are orthogonal to each other, so it can't be part of the pi system. It all makes perfect sense as long as we understand the structure of the molecule. Well, let's look at parole. Parole's kind of a similar situation. But it's not exactly the same, is it? Because if you look at the nitrogen on parole, there's no carbon-nitrogen double bond indicated like there was here on pyridine. So, what's going on? Well, we could draw another drawing similar to what I had done just a moment ago for pyridine, where we look carefully at all of the p orbitals associated with these atoms, assuming that they're all sp2 hybridized. So I'm going to assume that that nitrogen is sp2, and the bond to hydrogen will be out there. Now look at this sp2 nitrogen here. The nitrogen has 3 single bonds. They're very clearly shown here. And those are all resulting from various sp2 orbitals. Let's just draw one of them. We won't do it with all three bonds, but we'll just do it for this nitrogen-hydrogen bond here. There's an sp2 orbital on the nitrogen, which is overlapping with an atomic 1s orbital on hydrogen, and that overlap makes for the nitrogen-hydrogen single or sigma bond. So that's an sp2 orbital there, and that's an H1s orbital here, or a 1s orbital, and their overlap is what is the bond. Well, where's the lone pair? In this case, the lone pair is not in that sp2 orbital, that's for sure. That's already tied up in this bond, and there's another one tied up in a bond there, and another one tied up in a bond there. In this case, this lone pair must be sitting in the p orbital. And each of these other p orbitals have one electron in them. I know that just by looking at the structure, pi bond, pi bond. So if you look at the total pi system, there's 5 p orbitals with a total of 1, 2, 3, 4, and then the lone pair makes 5, 6 pi electrons. This is aromatic for sure. The molecule is aromatic because the lone pair sits in a p orbital, and in this case it is part of the pi system. In the case of pyridine, it was not part of the pi system, but in the case of perol, it is. Okay, that's all well and good. Let's look at furan now. One last molecule. Furan we'll try to draw its various p orbitals, assuming once again that the oxygen is sp2. If the oxygen is sp2, then it would have 3 sp2 orbitals associated with it. One is helping to make that sigma bond there, one is contributing to that sigma bond there, and the third one must be planar to those two, and it would be right out here. There's an sp2 orbital. If it's sp2 hybridized, all of the carbon atoms, or I should say all of the atoms around the ring, would have a p orbital associated with them, and it would be fully conjugated. So that's a p orbital right there. Well, if we look at this drawing, we can see that there's pi bonds there and there. That means there's an electron there, an electron there, an electron there, an electron there. There's your pi bonds. The oxygen has 2 lone pairs. One would have to be in the p orbital, and one would have to be in the sp2 orbital. If you look carefully now, you realize that the lone pair that's in the p orbital is part of the pi system, part of that conjugated pi system. It's one of the 5 atomic 2p orbitals that make the molecule fully conjugated. So there's 2, 4, 6 pi electrons. It's aromatic. What about the other lone pair? The other lone pair must be sitting in an sp2 orbital, which is once again orthogonal to the pi system. So how do I know these things are true? Well, it's because I know what it means to be sp2 hybridized, and I know what orbitals are involved, and the fact that I have a trigonal planar geometry with a p orbital that is perpendicular to the plane defined by the 3 sp2 orbitals that are making up the rest of the story. So, bottom line is, heteroaromatics can be aromatics. If they're called heteroaromatics, they must be aromatic, and they're aromatic for different reasons. Sometimes the lone pair is not part of the pi system, sometimes it is part of the pi system, and sometimes one is part of the pi system but not the other. We should be able to look at these molecules and figure out those structural details. Heteroaromatic molecules, an important part of organic chemistry. Well, let's continue this discussion about aromatic compounds by talking about the benzylic position. The benzylic position in an aromatic molecule is closely related to the idea of an allylic position. So recently, as we were discussing the effects of conjugation, we discovered that this allylic position is kind of special. The definition of an allylic carbon with allylic hydrogens is the following. There's an sp3 hybridized carbon, in this case one that bears hydrogens, attached directly to an sp2 pi system. Those two carbons are sp2 hybridized, And as we've been discussing with all these aromatic structures, these sp2 carbons will have a p orbital associated with them, these coming in and out of the plane of the board. Overlap of those two p orbitals accounts for the pi bond. So an allylic position is an sp3 carbon, with hydrogens in this case, directly attached to this alkene functional group. That's the allylic position. Benzylic is very closely related. It's the same idea, really. It's an sp3 carbon directly attached to a benzene ring. All of the carbons around the benzene ring are sp2 hybridized. The benzylic carbon is sp3. This is a simple molecule in which there's just one carbon, this methyl group, attached to the benzene ring. But you can have a more elaborate structure like this one where there's any number of carbons. Only the carbon that's directly attached to the ring is referred to as benzylic. These carbons out here are not benzylic. Only that one, the one that's directly attached to the sp2 hybridized carbon of the benzene ring. Well, why does that matter? Why do we care about this benzylic carbon? It turns out there's a very simple reason. That benzylic carbon does some chemistry, some very interesting chemistry. It can be oxidized. You might recognize this KMNO4. We've used this before. Potassium permanganate. Turns out potassium permanganate is a strong oxidant. And this particular reaction, which would take this methyl group at the benzylic position and oxidize it to a carboxylic acid, this is an important reaction. It makes this compound called benzoic acid. Those of you taking the lab would have used benzoic acid early in Organic Chemistry 1 lab, probably during a melting point experiment. It's an important aromatic carboxylic acid. So that's a reason that this is an important reaction. But from our perspective, it's also important because we realize that this oxidation is likely to be a free radical process, and the benzylic position is attacked or is oxidized selectively because it's going to involve a free radical which is resonance delocalized throughout this ring. So the benzylic position is special because if you produce an sp2 carbon, let's say by converting this to a free radical or converting this to a cation or even converting this to an anion, it then becomes part of a larger pi system. It's resonance delocalized. We don't have to worry about the mechanism of this reaction, but you do have to know that if you take potassium permanganate and treat it with a molecule like this, and here's the key, the molecule has to have a benzylic carbon, and that benzylic carbon must have at least one hydrogen attached to it. There has to be at least one benzylic carbon-hydrogen bond. If that is true, then that benzylic carbon will fully oxidize all the way to the carboxylic acid. You'll make benzoic acid. Even if you had a molecule like this with this very long hydrocarbon tail on it, this carbon right here is the benzylic position. That's the only one that's benzylic. None of the others is benzylic. And that benzylic carbon has two hydrogens. The requirement is that it has to have at least one. It's an sp3 hybridized carbon with at least one hydrogen. This one has two. It will be selectively oxidized at the benzylic position, and it will be oxidized all the way to this benzoic acid. The rest of this structure is essentially wasted in this reaction. We are oxidizing selectively at the benzylic acid. This just gets shredded aside. We produce benzoic acid. This reaction is somewhat wasteful because you're losing all those carbons. This would be a more atom economical reaction, but the key is that it is the benzylic position which can be readily oxidized by potassium permanganate. That's important. Now let me show you an example of another reaction, or at least attempted reaction. What if I took this molecule? Here I have a tertiary butyl group attached to a benzene ring. Right now there would be no reaction. Now why is that? I have a benzylic carbon, that's the one I've just bold-faced, but there's no hydrogen directly attached to it. There's only methyl groups attached to it. The requirement is that there has to be at least one hydrogen, one benzylic hydrogen, in order to get this oxidation to benzoic acid. And that's because, as you may remember from free radical processes, that the free radicals that are first formed are going to try to do a hydrogen atom abstraction, and it's easy to abstract a hydrogen from the benzylic position, like that one right there, because as we just stated, it forms a resonance delocalized free radical. It's much more difficult to abstract hydrogens from other positions, and so it just doesn't happen. So this one's no reaction, whereas both of these give the same product, benzoic acid. So that's important. Okay. Let's talk a little bit about some common aromatic structures. It turns out aromatic compounds have been studied for a long, long time. And many of them have been known for a long, long time. So long that they have these trivial or historic names associated with them. These are not IUPAC names, not at all. But it's important for us to know at least some of the most important trivial or historic names, because in the literature, including in your book and on exams, you're going to see these names, and so you need to know what they mean. If you have one methyl group attached to a benzene ring, that's called toluene. You've probably used toluene as a solvent in lab. If you have an aldehyde group attached to a benzene ring, that's called benzaldehyde. Very common aldehyde. There's benzoic acid. It's a carboxylic acid attached to a benzene ring, benzoic acid. And notice that in all these cases, it doesn't matter where you show the point of attachment. This carbon and this carbon and this carbon and this carbon and this one, they're all chemically identical to each other. We could be projecting these various functional groups at off of any of these carbon atoms. It's all the same. When you have an alcohol, an OH group attached to benzene, it's called phenol, which is an interesting name, phenol. If it's not an OH but an OCH3, it's called anisole. And finally, when there's two methyl groups attached to a benzene, it gets this name xylene. It is a dimethylbenzene, would be also an appropriate name, but the trivial or historic name that everybody refers to it is xylene. And xylene is spelled with an X, an interesting spelling. So that's very interesting. Well, xylene leads us to the question of, what about other isomers? So I want you to look at this. That's the very same xylene I just showed you, a dimethylbenzene. And down here is a different xylene. It's a dimethylbenzene, but instead of having a 1-2 arrangement of the methyl groups, I now have a 1-3 arrangement. 1, 2, 3, 4, 5, and 6. The methyl groups are 1-3. It's a 1-3 dimethylbenzene. And down here, it's a 1-4. 1, 2, 3, 4, 5, 6. It's a 1-4 arrangement of the methyl groups, a 1-4 dimethylbenzene. Well, it turns out that with di-substituted benzenes, we use a nomenclature called ortho, meta, para. Ortho, meta, para. Ortho refers to a 1-2 substitution pattern. Meta refers to a 1-3 substitution pattern. And para refers to a 1-4 substitution pattern. Now this only works when it's di-substituted. If you've got 3 or 4 or 5 substituents on there, you don't use ortho, meta, or para. It's only di-substituted benzene rings, di-substituted benzenes, that use these ortho, meta, or para prefixes. And when you put it in a name, you don't spell out the entire ortho, meta, or para name. You just use O or M or P. So for example, this one that we started with was a xylene in which the methyl groups are 1-2. We would refer to that as orthoxylene, and we would spell it this way, O-xylene. And down here, when they're 1-3, we'd call that metaxylene, M-xylene. In words, you still say meta. We wouldn't say M-xylene or O-xylene. We would say orthoxylene, but when we spell it, we just abbreviate with an O, or an M, or in this case, P for paraxylene. So ortho, meta, para is very commonly used when we're talking or working with di-substituted benzenes. So let's look at a couple of examples here. Let's try to name these compounds. Now, I've told you already that nomenclature is not my favorite topic, and we're past the point where I'm going to test you on nomenclature, that's for sure. But it is nonetheless important to understand nomenclature, because you're going to see the names of compounds in the book, on exams, in other places. I'm going to talk about them, and you need to know the language so that you can understand what the heck's going on. So let's look at this molecule. It's going to turn out there's going to be multiple ways to name each of these molecules, but we're going to use ortho, meta, and para here just to reinforce this recent learning. So these groups are located 1, 3 with respect to each other. 1, 2, 3, 4, 5, 6. What's 1, 3? Ortho, meta, or para? 1, 2 is ortho, 1, 3 is meta, and 1, 4 is para. So this is a meta arrangement of these two substituents. You see, they don't have to be the same substituent. They're clearly not in this case. How do you name this? Now, there really are a bunch of different ways you could do this, but one way is to sort of identify toluene as the base. See, so I've just circled toluene, leaving the bromine out, and I could refer to this as a meta-bromo-toluene. And that's a perfectly acceptable name. And that's generally the way these disubstituted aromatics would be named if there is some sort of trivial or historic name associated with some part of it, like the toluene part here. But when I go down to this molecule down here, I don't know how familiar you are with the nitro group, NO2, but you're going to become very familiar with it soon. The nitro group is a common functional group in organic chemistry. And this dinitrobenzene doesn't have a trivial or historic name, at least not that I'm aware of. But I do note that the nitro groups are para with respect to each other, so you could just simply call this para dinitrobenzene. And likewise down here, I'm not aware of a trivial or historic name for either iodobenzene or chlorobenzene, but I do note that these two substituents are ortho with respect to each other, and I'm just going to place their substituents according to alphabet, C before I, ortho, chloro, iodo, benzene. So this gives you 3 examples of the way we might name an aromatic molecule. In one case there was a trivial or historic name sort of buried in the structure, so we used that as the base name. In the other 2 cases there weren't, but there were still ortho and para designations to be had. We've covered a lot of ground. We've talked about aromatic molecules extensively. Our very last topic here is to talk about polycyclic aromatic hydrocarbons. Polycyclic aromatic hydrocarbons. It just simply means a whole bunch of aromatic structures tethered together somehow into a massive polycyclic aromatic hydrocarbon. I'm not going to go into much detail here, but I do want to mention that, as you've no doubt figured out by now, benzene is the prototypical aromatic structure and a very important one. It is possible to fuse 2 benzene rings together, and when you do that, you get naphthalene. And you can keep going. You can keep fusing aromatic rings together. When you get to 3, it's called anthracene, and etc. You can go to 4, which would be called a tetracene, 5, which would be called a pentacene. Those are actually interesting molecules. They're all, once you get to about tetracene and larger, they are examples of organic semiconductors, the sort of molecules that have been used to make organic electronic devices like we recently discussed in class. Well, these would be polycyclic. At least this one has got 3, so I guess it would be okay to call it a polycyclic aromatic hydrocarbon. One thing I wanted to note is that it is possible to start getting some unusual topography on molecules if you start piecing these benzene rings together in a certain way. So this is just naphthalene, same as that one. By the way, naphthalene is the compound that's in mothballs. So if you've ever smelled mothballs, it has a very peculiar odor, you're smelling naphthalene. Well, if I fuse the first 2 together like that and make naphthalene, if I went in a linear fashion, which means put the next ring here, I'd make anthracene, but if I don't do it in quite the same linear way, but instead I do it like this, then I make a molecule that's called phenanthrene. And if I continue in this vein, you see something interesting is happening. I'm sort of making a cyclic compound made up of cycles. But what you have to realize is that every one of these is a flat structure, or at least it should be. And so if I drew in the carbon-hydrogen bonds, those carbon-hydrogen bonds are starting to bump into those. Is it possible to keep going? Well, it is, but what would have to happen is that I would have to be lifting these benzene rings out of the plane in order that they weren't bumping into the ones down below. And I could just keep going and going. And I don't know if this looks familiar to you, but this is essentially a slinky. I'm getting this spiraling structure. I'm going to stop drawing there because I'm going to be overlapping so much one on top of the other that it gets confusing. But this is like a slinky toy. I'm sure you know what I'm talking about, the slinky that goes downstairs. If you've never used a slinky before or played with one going downstairs, you need to change that. That should be on your bucket list. Everyone needs to do that at least once. And so this spiraling structure is actually no longer flat. It's made up of flat rings, just like the slinky, but they kind of come up above each other and they just keep spiraling and spiraling. And the reason I point this out is not only because I like slinkies, but because it turns out this is an example of a spiraling compound. It spirals around, and this one happens to be spiraling in a clockwise direction, but we could have another compound that spirals in a counterclockwise direction, and look at those two spirals. They're mirror images of each other. In fact, they're non-superimposable mirror images. It turns out that once you give this a three-dimensional flavor, these spirals look like they're two-dimensional, but if you can imagine them as three-dimensional spirals like a slinky, these would actually be non-superimposable mirror images of each other. What the heck does that mean? That means they are a pair of enantiomers. Spiraling structures, as it turns out, are inherently chiral. This spiraling aromatic structure is inherently chiral. It exists as a molecule and its stereoisomer, a non-superimposable mirror image structure. It is one of the very few examples where you can have chirality in molecules without having any stereogenic centers. The topography of the molecule, the spiraling three-dimensional nature of it, makes it chiral. There's another molecule which spirals in sort of a double helical fashion. It's called DNA. DNA is also a chiral structure, not because it's loaded with stereogenic centers, but because of its topography, the same as this polycyclic aromatic hydrocarbon that looks like a slinky. So I know we've already studied stereochemistry, that was a while ago, but now that we're on to aromatics, I thought I would show you an example of a molecule that can be chiral even though it doesn't have stereogenic centers, and it is but one of many polycyclic aromatic hydrocarbons that have interesting features. Well, that concludes our studies of aromaticity. When I come back in person and see you next, we are going to get into the reactions that aromatic molecules, and in particular benzene, undergo, and that's going to be our next area of study. I'll see you then.